All right, so today we're going to talk about logarithmic differentiation. And the reason it fits in here is because you need to know how to take the derivatives of logs and exponentials for logarithmic differentiation to work. So first things first, I want to re-emphasize some of the rules about derivatives. Now, there are two rules about derivatives of things with exponents, all right? So if we have things with exponents, they can happen in two different ways. What am I looking for? My magic pen. We can have a derivative if I have an x to a power. The derivative of x to the n, you bring down the power, reduce it by 1, and x to the n minus 1. When you take the derivative of a to the x, the derivative of a to the x, there we go, is a to the x times ln a. So that's what happens when you have the derivative of a variable base and a constant exponent versus a constant base and a variable exponent. Okay? Now, what happens if you have something that doesn't fall into those categories? If you have something that has a variable base and a variable exponent, well, we don't have a rule for that, so what we do is we take the natural log of both sides, of course, or technically any other log base will do. You may think to yourself, oh my God, why would I introduce logarithms if I don't have to? Except if you're me, you're like, yay, logarithms. So try to be more like me and say, yay, logarithms, because they make everything easier. So let's say we want to take the derivative of x to the 3x. What we're going to do first is we're actually going to rewrite that, and we're going to write it as y equals, what am I looking for? Y equals, why is this still on the wrong thing? Hold on. Sorry, I'm having technological difficulties here. If I have y equals, there we go, x to the 3x, and I want to take the derivative, the first thing we do is we take the ln of both sides. So ln y equals ln x to the 3x. Well, the reason we do that is because now this exponent can fall down in front, and I have ln y equals 3x ln x. Now, when I go to take the derivative of both sides, I'm going to do so implicitly. So I'm going to take d dx of both sides. So over here, the derivative of ln y is going to be the derivative of the end over the end. But the derivative of y is technically 1 times dy dx. Now, I'm going to put the dy dx to the side because it makes my life a little bit easier. But you could also write it as dy dx on top right here. But again, you don't have to do it that way. So you can write it as 1 over y dy dx. Then on the right-hand side, I have a product rule. I have the first times the derivative of the second. The derivative of ln x is 1 over x. Plus the second times the derivative of the first. So if I want to solve for dy dx, dy dx equals y times, well, 3x times 1 over x is just 3, plus 3 ln x. And there's my derivative. Except here's the thing. We were told to take the derivative with respect to x of something in terms of x. So there's usually an implied idea here that we want our answer to be all in terms of x. So our derivative dy dx is y times this stuff. Well, here's the this stuff. But it says y. I don't want to write y. Well, I don't have to write y because look, here's what y is in terms of x. So I'm going to write y as x to the 3x. And my derivative is the original times 3 plus 3 ln x. So logarithmic differentiation is basically a way of giving a process to taking a derivative when you have a variable on the bottom and a variable in the exponent. So let's do it one more time down here. Example 2. I want to take the derivative of 2x to the x squared. If you're feeling good, if you're feeling smart today, take a second, pause the video, and then come back and check it out. But if you're not feeling too confident yet, watch me go through it. So I have d dx of 2x to the x squared. I got a variable base and a variable exponent. So y equals, let's see, 2x to the x squared. I'm going to take the ln of both sides. When I do that, I'm going to bring down the power just to save myself some room. So I have ln y equals ln of 2x to the x squared. I brought the x squared down in front. Now I'm going to take my derivative, d dx, d dx. Derivative over here, the derivative of ln y is the derivative of the end over the end. And then the derivative over here is a product rule. The first times the derivative of the second plus the second times the derivative of the first. So then if I solve for dy dx is y times, well, let's see, these 2's will cancel, that'll cancel with that. So this is really just x plus 2x ln 2x, which, long story short, becomes dy dx equals, what was y? 2x to the x squared times x plus 2x ln 2x. And that, my friends, is logarithmic differentiation. It has all the classics in it. We have to take the ln of both sides. We have to use a log law. We have to use a product rule. We technically have to use a chain rule. We're using implicit differentiation, and then we're using substitution at the end. It's everybody's greatest hits all shoved into one example. But there you go. If it's a variable base, variable exponent, you have to do this. It does not conform to the other rules. All right, I told you 6 minutes was my estimate for this video. 6:28, not too bad. Have a wonderful evening or morning or whatever time it is to you. Bye-bye.